Good afternoon. Welcome to the auditorium, and also welcome to any of you who may be watching from the comfort of your cabin. For those of you that didn't see my first presentation yesterday, my name is Ben Church. I'm a geologist, which is kind of important because with all the resources on this planet, if you can't grow it, you've got to dig it up. And with geology, we combine physics, chemistry, and biology to gain an understanding about the way in which the Earth works. And that's really what my first presentation was about, is the overarching theory of plate tectonics, the unifying theory of plate tectonics. Today's talk is a logical progression from that, the wonderful world of volcanoes. So if you have had a heavy lunch and you think you might snooze, be warned, you may well wake up with an explosion partway through. So my background is, yes, I'm a geologist. In a different life, I worked on oil rigs. I also was a teacher of both geology and geography for 26 years. But don't worry, it's not a lesson. There won't be a test at the end. I also lead adventure travel expeditions with young people and lead whistle-stop cultural and educational tours for American high school students, two very contrasting experiences. And I collect and sell Cornish mineral specimens. I'm lucky enough to live on the north coast of Cornwall. Yes, this is a geological talk, but later in the cruise I will be doing some talk about adventure travel as well. So, let's get started. We're going to start off with looking at the sort of basic classification of volcanoes. You have the three categories of, firstly, active. So an active volcano is one that has erupted within the current epoch, as geologists call it, so the Holocene, which is in the last 12,000 years. If it's actively erupting, well, at any one time, globally, there'll probably be about 50 volcanoes that have had a gap between the last eruption and the current one of less than 3 months. And at any one time, you're probably looking at about 20 eruptions on any given day. So I delayed coming up to the auditorium as long as possible because I was watching the news, because there is an imminent eruption on the Reykjanes Peninsula in the southwest of Iceland at Grindavik, and that is about to go. So watch this space on that one. A dormant volcano is one which isn't erupting now, and it may not have erupted for thousands of years, but potentially it's still active in the future. And the reason why it's still active in the future is that it is either on an active plate boundary or it is above a hotspot. So a good example of that was Mount St. Helens. Prior to 1980, hadn't erupted for 120 years, and then it went boom. An extinct volcano will never erupt again. There's no magma source underneath it due to plate tectonic movement. So this is Arthur's Seat in Edinburgh. So 1968, my first mountain at the age of 4. I refused all offers of assistance, and I think that was when the die was cast. So an extinct volcano then will never erupt again. It's not a hazard. Now, active and dormant volcanoes can both be a hazard. However, they're not all a hazard. Well, if we look at the distribution of them, which echoes the plate boundaries, they occur in active zones along those plate boundaries. And many of those plate boundaries are in very remote locations where there are few or no people at all. Might be in the middle of the ocean, for example. And if there's no people there, then it's not deemed to be a hazard. So the different plate tectonic environments produce different types of volcanic activity. So if you're not on a plate boundary, if you're on what's referred to as a hotspot, probably the most popular, well-known one would be the hotspot of Hawaii, but we also have the hotspot of Iceland, which also just so happens to be on a mid-oceanic ridge, which is why it's so active. We also have the oceanic island arcs. So an example of that is indeed the Caribbean, where we're going, where a piece of oceanic crust is being subducted or destroyed beneath another piece of oceanic crust. We then also have the oceanic continental one, so the one on the right-hand side there. So that's like the Mount St. Helens situation, where oceanic crust is going underneath continental crust, and you get a much more explosive eruption. So if you're above hotspots, like in Hawaii or in Iceland, somewhere like that, the volcanoes tend to have very shallow slopes, quite smooth and broad. and in fact they do have the name of shield volcanoes because of their shape. They tend to be non-explosive, what we term effusive, so you've got very fluid lava. Now, this lava then will be able to flow and run quite a long distance relatively quickly before it cools down, and that's how you get the low angle of slope on the volcano. Now, this might look very spectacular, so this was Iceland, High May, 1973, but what you're looking at here is this very fluid lava undergoing a sort of dramatic lava fountain. It can go hundreds of meters up into the air, but it's not very explosive. The main product of this kind of volcanic activity is the lava itself. If, however, you're looking at volcanic activity at one of the subduction zones, the destructive plate boundaries, then you have a different style of volcanic eruption. So if it's oceanic, then you get a sort of classic volcanic cone like Mount Fuji there, and the composition of the magma is different. It's richer in silica, and that makes it much more thick and sticky, viscous. So a viscous lava, or viscous magma, will produce a vicious or explosive eruption. These are the ones that go boom. So you get a different structure as well, in that you've got not just lava, but you've also got layers of volcanic ash, lapilli, which is like volcanic gravel, if you like, and then volcanic bombs, much larger pieces of rock and pieces of lava that have been ejected from the volcanic vent. Some of these can be as big as a transit van. If we go to the oceanic continental boundary, we get what's called a cordillera, a mountain chain along the coast of that continent. So, for example, the Andes. And this is even more viscous lava, even more explosive. So here we've got Mount St. Helens. And a measure of the explosivity is the Volcanic Explosivity Index. So most people are familiar with Mount St. Helens, so we're going to use that as a point of reference, and that has a volcanic explosivity index of 5. If you go up to 6, it's 10 times bigger, and so on. So, the viscous magma, thick and sticky, has a vicious eruption. Now, the reason for that is because this high viscosity makes it difficult for the gas bubbles to escape. As the magma rises, there is less pressure on it. So all of the dissolved gases, so carbon dioxide, sulfur dioxide, and indeed water vapor, our atmosphere and all the water on this planet came out of volcanoes. All of that is trying to escape, and it's forming bubbles. Now, if it's thick and sticky, those bubbles can't escape. You get a build-up of pressure, and then you get a very explosive eruption. So the thicker and stickier it is, then the more explosive it will be. And that means that the product of the volcano will also be different. So it's not just lava, you're getting a lot of volcanic ash, which is the fine stuff, less than 2 millimeters, and then this lapilli, the gravel that I mentioned, and then also the big volcanic bombs. So, I did promise you an explosion. Now, this is a really nice, it's short, but it's a really good little clip. Wait for it. Just trust me on this. Wait for it. Also, look at what happens to the clouds.
Watch out for the shock, it's coming. Holy smoking Toledos.
Fantastic. I love that clip. So, an explosive eruption because of the thick, sticky, the viscous magma. So, if you look at the fatalities that you get with volcanic eruptions, look at these two here. So we've got the Tambora eruption in Indonesia. That was the loudest explosion anybody's ever heard. People within 40 miles of it had their eardrums burst by it. Now we're talking about 180 decibels. And then Lakey in Iceland, 1783. Now both of them, we had large death tolls because of starvation. Now, that's a historical thing. That wouldn't happen now because in the modern world, of course, we can send aid and so on. If we look at the primary volcanic hazards, which is what actually happens in an eruption, The biggest killer there tends to be what we call pyroclastic flows, more of which in a moment. The secondary hazards are ones that happen as a result of the eruption. With them, it's the mud flows, technically termed lahars, which are the biggest killer. They kill about 37% of all the deaths since in the last century. But these pyroclastic flows, they've caused half the deaths in the last 100 years or so. But to put that in perspective, on average, you're looking at maybe 1,000 deaths a year from volcanoes. Earthquakes, maybe 200,000 a year. Car crashes, 1.35 million. So, let's look at these primary hazards in a little bit more detail. We'll start off with the obvious one, with lavas. So a basalt lava, like this one here, would be erupted at somewhere between 1100 and 1300 degrees centigrade. Some of the thicker, stickier lavas are at slightly lower temperature, maybe as low as 800. You can see the surface texture here, which is similar to the one that was by my feet on the introductory slide. And it looks a bit ropey. And it's got a special name, which is pahoehoe, which is the Hawaiian name for ropey. They do also have lavas where this crust, which is a bit like the thick skin on custard, has been broken up by escaping gas. And then it's all angular and sharp. So then it's called a'a, which is Hawaiian for painful to walk on. So in Hawaii, eruptions do destroy property, so you can see here the damage to roads and so on. Luckily, there was nobody in the school bus at the time, I'm reliably informed. Of course, as soon as that lava at maybe 1,000 degrees gets anywhere near to vegetation, it'll be up in a puff of smoke, as will your house be. However, generally speaking, people can escape. So it tends to be damage to property rather than fatalities. Here we've got Kilauea erupting in Hawaii in 1983. Very spectacular. Destroyed about 80 houses, but nobody was seriously hurt. This eruption has actually added significant areas of land to the island. And of course, it's a fantastic tourist attraction as well. So I wonder if anybody can tell me what one of the main tourist attractions is in Rwanda. Well, I can tell you. That's me on the left there with less fat and more hair. It's these silverback mountain gorillas. Fantastic. So this was in 1988. I was exploring in the area in the Ngorongoro volcano. Now, that I will cover at greater length in a future talk called When the Going Gets Tough, It Makes a Good Bar Story, because no one wants to hear when everything goes right. They want to hear all the stuff where you get bitten or chased or whatever, and that happens to me quite a lot. But on this volcano then, it's just near the Rwanda border. It's on what's called a hotspot. So there's a rising plume of magma which has domed the crust above it and split it into a three-armed rift. And that's where we have this volcanic activity. The main crater is a couple of kilometers wide, and usually there's a continuous lava lake there. Now, in January of 1977, the walls of that crater fractured, and this lava lake drained in less than an hour. So you had this very liquid lava screaming down the side of the volcano, very, very fluid, overwhelmed villages, and over 70 people died. Spookily, almost exactly 25 years later, same time of year, January, this time 2002, you had another eruption here. This was a fissure eruption where it's along a long crack rather than from a central point. And this was on the southern flank of the volcano, and you had a lava flow between 200 meters and up to a kilometer wide going towards the town of Goma. And it was up to a couple of meters thick, and it destroyed 14 villages on the way there, and roughly 150 people died. What was interesting here, though, is the way in which the people died here. About 150 of the people that died were asphyxiated by by gases, by carbon dioxide, more of which in a moment. So with the Goma eruption, you had about 4,500 buildings destroyed, and there were fires and earthquakes for months afterwards. However, this was an example of a successful prediction. There were warnings. Primarily, the main warning for volcanic eruptions is earthquakes, more of which later. They've certainly been having plenty of them in Iceland in the last month. And this allowed the evacuation of 400,000 people, which drastically reduced the death toll. So if you look on a geological timescale, all of that I've just gone through, small fry. There are what are known as flood basalt provinces, those shown in red on the map there. These are mega eruptions. There hasn't been one in human history. The last one was about 15 million years ago in the United States. The biggest one is the Deccan Traps in India. You're talking about 1 million cubic kilometers of lava. So that's an enormous amount of lava. And it went on for a really, really long time. And also, it released a lot of gas. And it's thought that this may well be related to the extinction of the dinosaurs. And again, I'll talk about that later on in my meteors and dinosaurs talk. So, the biggest killer I mentioned with these primary hazards is the pyroclastic flows. So there's no sound on this one, by the way. This is Unzun in Japan. A pyroclastic flow, also known as a nube ardente, a glowing cloud of volcanic ash, dust, lapilli, volcanic bombs. We're talking about hundreds of degrees centigrade, a lot of carbon dioxide, a lot of sulfur dioxide, and these are fast. They can go well over 50 kilometers per hour. You'll be glad to hear that these people did actually escape. I checked that before I showed the video. But can you imagine how terrifying that would be? So, oh, there we go. This is another example of successful prediction and evacuation. So this was 1991, Mount Pinatubo in the Philippines. It's an island arc volcano. If we remember that Mount St. Helens was a VEI of 5, this was a VEI of 6, so that's 10 times greater. So a really major eruption. The eruption column up to 20, 25 kilometers high, these pyroclastic flows screaming down the sides of the mountains and extending for up to 4 kilometers away from the summit. They tend to destroy pretty much everything in their path. The main killer here, I mean, there were some deaths. I think the total number of deaths was 722, something like that. But about 300 of those were caused by roof collapse, because you get, in that kind of environment, you tend to quite often have flat roofs, and the ash accumulates on top of these roofs, and they collapse. But because of the prediction, they were able to evacuate 60 or 70,000 people, and that really limited the death toll. So, Iceland, back to one of my favourite places. So, newsreaders really struggled with this in 2010. Eyjafjallajökull. There you go, Eyjafjallajökull. Okay? Islands, mountains, glacier, it means. So, an explosive eruption, but it was only VEI 4, so 10 times smaller than Mount St. Helens. Pretty small. But normally that wouldn't really be any great shakes. It's likely that the imminent eruption in Iceland at the moment is going to be a similar kind of thing. But this one was a perfect storm. Perfect storm for 4 main reasons. First of all, directly under the jet stream. Secondly, the explosive power of this eruption was able to inject the volcanic ash straight up directly into that jet stream. Thirdly, the jet stream was on an unusual, stable path, a southeasterly heading. And fourthly, the eruption took place underneath 200 meters of glacial ice. Now, this gave it a bit more explosive power, but what's really important is that it meant that it produced this cloud of highly abrasive, very, very fine, glass-rich volcanic ash. And we all know what happened then. So we had all this huge ash cloud all the way over Europe, some of the busiest airspace in the world. We had weeks and weeks of disruption. The primary thing was about a week, 10 days. 10 million travelers affected. Why? I mentioned the tiny fragments of volcanic glass. They're abrasive. They get into the blades of the compressor in a jet engine, and then the ash melts in the combustion chamber, coats the turbine blades, and then the aeroplane will stall. So not very good situation to be in. So I'd like you to think about in 1982, there was a British Airways flight, 747 flight, heading from London towards Australia and New Zealand, and Mount Galunggung in Indonesia was erupting, and the passenger cabin started to fill up with smoke. Now, this guy, the master of understatement, Captain Eric Moody, made an announcement. Ladies and gentlemen, this is your captain speaking. We have a small problem. All 4 of our engines have stopped. We are doing our damnedest to get them going again. I trust that you're not in too much distress. Well, descending out of the ash cloud, the molten ash that had solidified enough, and it broke off some of the innards of the engines and allowed a smooth enough airflow for old Eric Moody to restart 3 of his engines. But they'd been gliding in a 747 for 15 minutes. What would you have said to your neighbour then? The longest glide in history of a non-purpose-built gliding aircraft. Incredible. Amazing coincidence. I've just come off the Balmoral, and at the end of this talk, a chap came up to talk to me. He goes, I used to fly with Eric. And he says that wherever Eric goes, in Australia, New Zealand, he never has to buy a beer. And he's dined out on the bar story for the rest of his life. Fantastic. So, there we go. Less fat, more hair again. Back to Iceland and Eyjafjallajökull. So, in 1982 there, that's me with a very old school friend of mine, Steph. And then fast forward to 2010, he's getting married in Uganda. So I went out to Uganda for the wedding, and I got marooned for 3 days by the ash cloud. Well, seeking opportunity in crisis, and thinking, well, I could choose. I could choose to be really depressed about it, or I could choose, well, actually, I've got an opportunity here. So I chose the opportunity, went on safari, and I took some humorous photos, let's say, of lions. And I entered them into a competition, and I won some tickets to the Adventure Travel Show in Olympia in London. And I took my gorgeous girlfriend Callie along, and we both filled in lots of competition forms. And a couple of weeks later, I got an email saying, oh, Mr. Church, congratulations. You've won the competition. Fantastic. Now, this is the ultimate synchronicity. The prize was all expenses paid holiday in Iceland. So, still in Africa, I mentioned with Goma the volcanic gas, the carbon dioxide. This is the volcano that burped. So we're talking about Lake Nyos. Now, Lake Nyos is in the northwest part of Cameroon in West Africa. It's a pretty big volcano. And again, it's in an area which is volcanically active because it's on one of these 3-armed rifts above a hotspot. Now, the magma is very deep below the surface, maybe 80 kilometers below the surface. But although it hasn't erupted for a long time, it has been leaking carbon dioxide for a long time. And it travels up through cracks and fissures in the rocks in the vent of the volcano. And there's a big lake there, Lake Nyos, deep lake, a couple of 100 meters deep. And in the cold water at the bottom, the carbon dioxide stays there and it's stored. But the lake is thermally stratified, meaning that the upper layer is warm and it just sits on top of, floats on top of, the denser, cooler layer below. Now, in 1986, there was a small landslide, possibly triggered by magma movement at depth, causing a little tremor, a small earthquake. This landslide put lots of material down into the lake, disturbed this layering, and the turbulence allowed all of this stored carbon dioxide, 1.6 million tons of it, to come bubbling up out of the lake. So you had 1.2 cubic kilometers of carbon dioxide gas released, and it spilled down over the side of the volcano. And you can't hear it, you can't see it, you can't smell it. And it's moving at maybe 25, 40, 50 kilometers per hour. Well, sadly, 1,700 people died, but they wouldn't have known anything about it. A lot of livestock were also killed by this. What they do now is that they have pumps that they lift water from the deep cold water up to the warmer water, and you have a constant steady release of it to prevent it happening again. Right, back to Iceland again. Remember Laki and the 1783 eruption where so many people starved? Well, in this eruption, it was the biggest historical eruption, took nearly 15 cubic kilometers of basaltic lava. And while some property was damaged, the main problem here was that the volcano released not only 122 million tons of sulfur dioxide, which when released into the atmosphere will give you easy for you to say, sulfuric acid aerosols, which can lead to acid rain, and that would have stayed in the atmosphere for a couple of years. But also a lot of fluorine, 8 million tons of fluorine. And when that contaminated all of the pastures, 75% of the sheep and half of the cattle died. And indirectly, thanks to starvation, 20% of the population of Iceland died. So, we talked about the primary hazards. If we think about secondary hazards, the big secondary hazard is the lahar, the mud flow. And the example I'm going to look at here is Nevado del Ruiz. This was 1985 in Colombia, big mountain. We've got a subduction zone, so it's a similar sort of style of volcano, if you like, to Mount St. Helens. However, it was only VEI 3, so it was even smaller than Najdafjörður. So the explosivity is not really a very reliable indicator of the degree of hazard. Notice that the summit is under snow and ice, and it's steep. So when you had the eruption, all of that snow and ice melted, and millions of cubic meters of water were mixed with a huge volume of volcanic ash. And this dense slurry, imagine hot, freshly mixed concrete, traveling at 60 kilometers per hour. Came screaming down the volcano. It also got concentrated into 6 river valleys, and the town of Armero, which was 20 kilometers away, was overwhelmed by these lahars, and over 22,000 people died as a result. So lahars are very, very nasty. Another secondary hazard is the secondary hazard of a tsunami. So these can be generated when you have a submarine eruption, or when you have a volcano where the top of the volcano, basically when the magma chamber has emptied, the top of the volcano collapses into the volcano, forming what's called a caldera, which means like a cauldron. And then if all the sea rushes in and then rushes out, it's going to cause a big wave. So if you look at 1883, Krakatoa, 36,000 people died there, and the vast majority of them were not due to lava, they weren't due to ash, they weren't due to lahars. It was because of tsunamis affecting the coastal towns. So you can see why it's called an island arc. All of the red triangles there are volcanoes. So on the day that the Krakatoa erupted, you had these 4 enormous explosions. You could hear them 3,500 kilometers away in Australia. All of the coastal towns on the Sunda Strait there, they were destroyed within a couple of hours. No survivors on the island of Sabesi. Everybody wiped out. And this was 13 kilometers away. So most of the deaths then were from this tsunami, and it was enormously powerful. There was a Dutch Navy ship called the Bearu, and it got washed 3 kilometers up the river, and there were still bits of it rusting away there in the 1980s. Now, all of that ash in the atmosphere blocked out a lot of the sunlight. The global temperature dropped by 1.2 degrees. That eruption darkened the skies worldwide, globally, for years afterwards. Silver lining, beautiful sunsets. So you had these incredible sunsets. This is by William Ashcroft. He did thousands of colour sketches of these red sunsets, but British artist. So he was halfway around the world. I'm sure you're all familiar with this painting. It's the right time. It's an accurate description, Munch's The Scream, an accurate description of what the sky over Norway may well have looked like after Krakatoa. More recently, in January of last year, we had in Tonga we had a big eruption. This was a submarine eruption, 65 kilometres off the coast. In fact, luckily, a very low death toll. I think 5 people died in total. But it was unusual in that it was a 2-part tsunami. So first of all, you had this huge shock wave, which resonated with the surface of the water, generated waves. The second shock wave, though, was the result of the displacement of the water by the eruption. And this was an hour later. And the initial wave would have been enormous. Very impressive indeed. So, it's not all doom, gloom, death and destruction, ladies and gentlemen. Volcanoes, they're not all bad. There are some good things about volcanoes too. So, for example, I like to travel, and in Southeast Asia, you've got areas like this with terraced fields, incredibly fertile soils. So often you're getting multiple crops a year. In Bali, they say if you stick a walking stick in the ground and walk away, you come back next year, there'll be a tree there. So the reason for this is that the physical and chemical breakdown of the volcanic ash releases lots of nutrients. And you very quickly get a fertile soil. Of course, to have a really fertile soil, you also need the organic element as well. But all around the world, you've got civilizations that were founded on very fertile volcanic soils. So you can look at the ancient Greeks and the Romans settling on the fertile volcanic soils of the Aegean region. You've got all of the Indonesian area there. And you can talk about the Etna with its olives, or if you go to the Canaries, they're growing vines on the slopes of volcanoes, all because of these very fertile soils. We have geothermal energy, and they're using bulldozers to make a great big earth bank, a gravel bank, around a geothermal power station in Iceland as we speak to try to protect it. So there are places around the world where you have a lot of underground heat, so Hawaii, New Zealand, Japan, Iceland, and what you can do is you can drill down and you can extract the hot water that is circulating at depth. Now, this hot water at depth can be several hundred degrees centigrade, maybe 600-700 degrees centigrade in Iceland. By the time they get it up to the surface, it's maybe a couple of hundred degrees centigrade. And what they do is they will put it in pipes like these, and very heavily insulated, and that will go to the towns and cities and be used for space heating. So that is one way that you can use your geothermal energy. The other way is that you use this water at 200 degrees C to generate steam, and that steam is then used to turn turbines, which gives you a very clean form of electricity. You also get a lot of natural resources from volcanoes. Say, can't grow it, got to dig it up. So this is 1992 in Indonesia on Gunung Merapi, where all the sulfur is there. And as you were walking around there, you could really feel a bit of a stinging in your nose. And that's because the sulfur dioxide, which was so rich in the atmosphere there, was dissolving in the fluid in your nose and turning into acid. So that was quite interesting. But that sulfur is such a valuable resource, used in fertilizers, insecticides, medicines, shampoos, batteries, all sorts of stuff. Basalt. So that hard, dense rock that makes up the ocean floors and is common in many volcanoes around the world, it's hard, so you could use it as a roadstone. Or if you get volcanic froth, so if you get the lava, which is basically more bubbles, more gas vesicles than lava itself, it can float. So this is pumice. Many of you might have a bit of this in the bathroom, great for removing bits of dead skin. If anybody's ever worn a pair of stonewashed jeans, They're the stones that you put in to get that faded effect. Down at the bottom left, I mentioned right at the beginning of my talk that I used to work on oil rigs. Well, when you're drilling an oil rig, you need mud. Not just any old mud. It's a highly sophisticated physical and chemical property mud, which is used to lubricate the bit, to turn the bit, and also to carry all of the cuttings back up to the surface. And that's what my job was to look at those cuttings when I was on an oil rig. So we use a particular type of clay for the drilling mud clay. My favourite type of clay, bentonite. I kid you not. This clay is also very absorbent, so sometimes they use it in cat litters and so on. And then on the bottom right, obsidian. This is volcanic glass. Now, if you broke a piece of obsidian and you looked at it underneath a very powerful microscope next to a surgeon's scalpel, in comparison, the surgeon's scalpel would look like a saw blade, whereas the obsidian would be almost completely smooth. It's so sharp that they still sometimes use it in eye surgery and in cosmetic surgery because it's such a fine cut, leaves no scar. Concrete. What have the Romans ever done for us? Well, they discovered concrete by mixing granular volcanic ash together with lime cement. So this new, strong, water-resistant material. So the Pantheon Dome, the world's largest and oldest unreinforced concrete dome. Incredible technology. So they built all sorts of fantastic buildings and waterworks, aqueducts and all sorts using their newly discovered concrete. Tourism is also benefited a great deal from volcanic activity. So this is the Blue Lagoon in Reykjavik in Iceland, currently closed, I'm afraid. So this is where you've got hot springs, where you've got hot water from depth arriving at the surface, often rich in dissolved minerals, and lots of people will tell you that this is great for curing ailments, or it's good for your skin. And you can spend eye-watering amounts of money on mud packs and face creams made from the mud at the Blue Lagoon. Kilimanjaro is a volcano. So the top left is 1988, and then bottom right then in 2014. So very popular to climb these big mountains. And for less economically developed countries with a weak economy, this is a fantastic way that they can generate money. People will pay a considerable amount of money to go up the mountains such as Kilimanjaro, and you have to have local guides. If you go to New Zealand, you can go to see Rapahoi. You can go skiing on a volcano, although they do occasionally have to close the ski slopes when there's an eruption. And still in New Zealand, if you're a big fan of Tolkien and Lord of the Rings, you can go to Mount Doom and Mordor. So go on a Hobbiton tour. So fascinating stuff. And in the areas, some of these areas, they were ecologically very, very sensitive. So in some areas, when they were filming, they actually put carpet down to protect the ground from the footprints of the film crews and the actors and the orcs and the elves, all of them. So tourists also like to marvel at just the sheer wonder of volcanic eruptions. So whether you're in Mauna Loa in Hawaii, which is a reliable performer, or Etna in Sicily, another popular location, lots of people like to go and have a look at these wonders of nature. Truly, truly beautiful places. And you can even go volcano boarding. So this was in Nicaragua, where you hop on a volcano board and go screaming down the side of the volcano. And by the time you get to the bottom, you look like one of those old-fashioned train drivers when you take your goggles off with a completely black face and white eyes. So marvellous fun. I do love volcanoes. Now for the test. Question 1. No, I'm kidding. Just a few takeaways for you so that you've got something perhaps that you might want to discuss over dinner. Number 1, remember, if it's viscous, thick and sticky lava, you're likely to get a vicious eruption. It's going to be more explosive. So that's the volcanoes around the Pacific Ring of Fire on the destructive plate boundaries. Secondly, the biggest primary hazard, when a volcano is actually erupting, are these pyroclastic flows, these glowing clouds of ash and dust and gases at hundreds of degrees centigrade and at high speed. The third point is that the biggest secondary hazard is the lahar, which you might remember is the mud flow, so like hot concrete flying down the side, cement flying down the side of the volcano. Fourthly, that volcanoes aren't that deadly. They kill less than 1% the number of people that earthquakes kill. Fifthly, it's pronounced Eyjafjallajökull. And finally, last point, that they're not all bad. You've got fertile soils, you've got geothermal power, you've got minerals, you've got tourism. Wonderful stuff. So, my next talk is in a few days' time. It's going to be about Barbados. Do check the Daily Times for details, just to be absolutely sure of that, because things can change. If you have any questions, I will be at the back outside the auditorium if you want to have a chat with me then. Or if you think of your question 5 minutes, 5 hours, or 5 days later, just catch me around the ship. I really look forward to talking to you. And thank you to the techs, and thank you for listening. Thank you.